finish off our discussion of the op-amp, which I hope to do today, but it may run over. So, in this lecture I will finish all the things that I didn't finish last lecture, so if you've got lecture 4's notes, other than a few typos, they are basically lecture 5 notes as well, but I've given out a new set anyway. We were discussing the problems with the original circuit, which I have here on the board. And you've seen this slide before and the one that follows it. But to recap, half of the differential signal is wasted. That's to say, a current flows down here which generates a voltage across this resistance that produces a current flowing into T3, or if you don't fancy that, a voltage across T3's facing this junction, and that in turn causes the current to flow through RVAS, which causes the voltage to be dropped across RVAS, which drives this push-pull at the end. But the other half of the current that's in this differential amplifier ends up going down this leg, and it just goes into the minus rail, and we don't see it again, and it doesn't do us any good. And in the last lecture we discussed current mirrors for a fair while, and we said that if you adjusted it into a current mirror setup, you could get that other half of the signal back, and you'd end up with twice the gain that you would have just a resistive load. Then we talked about the balance in the two legs, the current balance in the two legs of the differential amplifier. And I said that the current that flows into T3, due to the quiescent current flowing in this collector, so some quiescent current flows in this collector, there is a HFE at approximately 100, so some base current must flow. That base current has to come from T1's collector, and it doesn't, no similar current flows in T2's collector. So the current that's in this resistor is the current in there less the DC biasing current that goes that way. And that's not the same for T2. That upsets the balance in the differential pair, and the result of that is that we get a DC offset at the output, even when there's no input. And the current mirror should balance out this, the ratio of these two currents, the two collector currents, in order that the DC offset at the output is much reduced. And the third one is that the current that flows into T1 and T2's base in order to bias them. So this is the current. If you've been in the amplifier lab and you've not connected the V plus to anything at all, you turn it on, the amplifier output is 15 or minus 15. That's because there's no biasing current available to turn on this transistor. As a consequence, there is imbalance in the differential pair. A voltage appears across this resistor doesn't really exist, because in the amplifier lab it's actually an op-amp that does this job, because it's a bit easier. The lab's only 3 days long anyway. Some might argue it's actually 4. Depends how long you have to stay. So there's some current that has to flow into these transistors to bias them. If you don't like the idea of where it comes from, there must be a quiescent collector current. They both have a HFE, so there must be some DC base current to make them go. That's what I mean by the biasing current. The current we require is actually quite large, and that's proportional to, in the case of signals, there is a biasing current, and there is a current which is the signal current. And that signal current is related to a VBE, and those two go together in the transistor equation. When I say there is a base current, that implies there is a VBE as well. That is to say 0.7 and a little signal on top. And there is a constant base current, and there is a little signal on top of that as well. The size of that little signal is actually quite big. And another way of thinking about that is, well, if I try to drive a voltage, I try to drive a current in, and I measure the voltage that I need to drive that current, then I divide one by the other, I can get the resistance looking in. That resistance is a bit small. If you've got a commercial op-amp, you'll find the input resistance looking into the inverting and non-inverting inputs in the order of 100 megohms to a gigaohm. The input resistance looking into this circuit is probably in the order of tens of kiloohms. So there's an awful lot we can do. And it turns out that adding a current mirror down here greatly increases the effective size of this resistor, and greatly increases the apparent resistance looking into the base of T1 and T2. Moving on from the differential amplifier for a bit, there's this resistor here and a VBE here, and there's an IB there. So there must be a resistance looking that way. We divide the V and the I. R is V upon I. So this resistor and the resistance looking in there are in parallel with each other. If we make this resistor much, much bigger by using a current mirror, we can end up in a situation where the overall gain at this stage is bigger and the input resistance looking that way is still just the RBE. But we can do something to T3 as well. We can actually put another transistor just up here to make a Darlington. In my diagrams it's T8. So, one current mirror. And one Darlington. The use of the Darlington increases the impedance looking in the, resistance. They are, everywhere I say resistance, just insert impedance. And if I accidentally say impedance, switch it for resistance. Because we haven't dealt with any capacitances in this circuit at all. And actually it's full of them. But that has to wait for another year. So the resistance looking in here has gone up by a function of the HFE of these two, approximately multiplied together. And if you go back into Lecture 4's notes, I derived, I think incorrectly, an expression, so I sent out some new notes by email. I take it you've got them. 2 yeses, so it must be true. 1 yes, could be the only example in the universe. 2 yeses, definitely loads and loads of them. Goes for alien life as well, so I'm looking forward to the second finding, obviously after myself. So then we've got this resistor RVAS, and this loads the differential, Darlington pair, which is secretly just a common-emitter amplifier with no degeneration. If we were to make this into the current source, we would allow ourselves a very high resistance looking up here. At the moment, the resistance looking up there is just this resistor, RVS, whatever its value is. If we have a current source there instead, we will see approximately the RCE of the transistor, which will be in the order of hundreds of kiloohms. This resistor cannot be more than about, 500 ohms to 2 kiloohms, I would imagine, because we need about 1 to 5 milliamps flowing down this pathway. If it was a discrete audio amplifier, if it was a operational amplifier, it was integrated circuit, we'd probably have in the order of 200 microamps, I would have thought. Even with 200 microamps, if this is 15 volts and we assume no signal conditions, this will be at about 0.7, so we can work out what the value of the resistor will be, and it'll actually be quite small. That isn't the biggest value that it can be, but it's the right order. And then there are some other things that we haven't discussed yet, which are to do with the output stage, and they are, in my opinion, quite tricky, because a lot of what we've said so far invites you to think about the transistor as a thing that does amplifying of either current or voltage, and if it does both, then power. But actually, a more holistic approach is to think about it as just a mechanism of making resistors look like they've got different sizes. So if I was a signal here, I would see this resistance as a different size to what its value is. And if I was a signal here, I would see the resistance looking out of this node up there and down there as a different size to what they really are. The transistor is really just an impedance transformer. It's a thing for making resistances and capacitances and inductances look like they've got different impedances. If you need to prove that to yourself, and I think you ought to, set up either common base, common emitter, emitter follower, anything you like, drive a signal into its output, and find out what resistance you see looking out of the terminal that you're not interested in. So if it's common emitter, you drive the base, have a look at the impedance, and then you drive the collector and have a look at the impedance, resistance, or drive the emitter if you prefer, and convince yourself the resistances you see looking into this terminal are modifications of the resistances that are actually attached to the other terminals. Some of the examples that I've given, there's one in today's and there's one in lecture 4's. Actually, the one in today's is just a copy of one that's in lecture 4 as well, because we didn't get around to it. That's all we're really doing in a lot of those examples, is figuring out what resistances we see looking into certain points in the circuit. So if I was a signal here, I would see a certain fraction of this resistance. And if I was a signal being driven into this circuit, I would see a resistance that represents everything. And in the last part of day 3 of the amplifier lab, you were putting a, if you've not done it yet, then it's a bit of a giveaway, but generally speaking, on the second week, people turn up with some numbers and no idea how they got them. So I know where they come from. You can't really get past me that easily. You were putting a 10 ohm on here and measuring the voltage, the potential division on this node, and there was some question as to where the feedback went and whether the op-amp could see what was going on or not. What we were really doing there was measuring the output resistance, but instead of driving a signal in, we were making a potential divider between the amplifier and the resistor that we were using to load it. And the reason 10 ohms makes a nice value is that for the amplifier that's in that lab, the output impedance is about, output resistance is about 10 ohms. So when you put 10 ohms on and you had 2 volts coming out of your amplifier, it went down to about 1, and then you could do some Thevenin type stuff from 118 or 117. So this really is just a mechanism of resistance transformation. Another way of thinking about it is to say, well, there is a voltage here, this is the same, and while one of these is turned on, that almost the same voltage is presented to this resistance. The only difference is that a large current can flow down here, and into the ground, or if not this transistor on, if this transistor's on, into the minus rail like that, out of the ground. So we have a voltage here which is in control of a voltage here, and there is a pathway for a large current to flow which otherwise didn't exist. A large current can't flow off this node because it has to flow through this resistor, which is pretty big. And if it did, there'd be a big voltage drop across the resistor, and that would screw up our DC conditions. So you can either think about it as, oh, well, I'm making this impedance look at resistance look a different size, or you can say, oh, it's a current amplifier. The truth of the matter is they are the same thing, just expressed differently. You have to convince yourselves of that one as well. If you haven't started doing the problem sheet, it would be a pretty good idea, because this is the last lecture that we do this sort of thing. The other thing you've got to do is the examples I've given are not verbatim and they won't come up on the exam. You've got to do a few of your own to make sure that you're well oiled in the techniques, because the technique is the important thing. The answer is basically irrelevant, more or less. Unless you've got a specific problem in mind, in which case the answer is very important. Right, last thing. So to summarise what I just said about these two, the source impedance, which is the resistance looking out of here, affects how this transistor views this resistor, and the size of this resistor affects how this stage views this stage. All the resistances and impedances are linked. The trick is knowing when you can draw the lines and say, well, this bit's basically isolated from this bit, so I can make these assumptions. That's the trick of the designer. So last thing, T4 and T5, there's a bit in the middle of the signal where they're switched off, so you end up with this. Wow, that's bad graph. There you go. Flat bit, flat bit, flat bit, flat bit. This is time. Volts across the external load. So these flat bits are due to neither of these transistors being conducting at a certain point, and this is day 3 of the amplifier lab as well. And we could insert a little circuit in this box to make it go. And it looks like this. Sorry. I had a history teacher who could do that at will. I can only do it by accident. So I think he's retired now, but it's much more likely that he's dead. So we put a little circuit in, and we'll discuss this in this lecture. And once we've discussed everything, so that, the impedance is here, this current source, we were halfway through when we stopped last time, then we'll be done with the amplifier. But that is by no means a complete summary of the design of analog circuits. There is so much that's left out, it's almost inconceivable to start conceiving it. So this is the last slide from the last lecture, and I just about got down to the DC conditions using the circuit on the left, and I hadn't really started talking about the small signal model. So, how does this bit work again? Give you a biscuit. Is it really that early? Okay. So there's, well, if you were feeding either astute or pedantic, you could say, oh, it's a common base amplifier, which it would be if we drove a signal in here, but we don't. But you can see on the small signal model the base is grounded. It's not actually doing the job of an amplifier, it's just trying to make a constant current. So we bias a VB here, and 0.7 of that VB ends up across this base emitter junction, and the rest of it, so VB less 0.7, ends up across RE. And we can choose RE at will, we just pick a value, and then go to the drawer and find that somebody's put the wrong value back in the drawer and swear loudly. The result of this is a current IE which is defined by the value of RE and the size of VB, taking into account the 0.7. And then we'd assume that the base current's negligible, or if it's not, we'll write some equations and add it in. And then we'll have a collector current which is essentially defined. Now it's not perfect by any means, and if you stick around long enough you'll find there's a little capacitance in there that allows the signal here to get up to here, but I don't want to get into any of that. Just assume it's perfect for now. And it can be represented by the small signal model on the left, right. Yes, I have 3 degrees. That's the right. It is my left though, so I feel justified. Right, to find out how it will react to a signal, because the signals will be down here. We'll have some signals going up and down on this node. There'll be a signal here, and what we'll have here is just a voltage bigger than that. There won't be anything special about them, they'll be in phase and everything. One like that, one like that. The ground for this one is maybe, I'll put it in the middle, the ground for this one is somewhat below. So this one is pushed up a bit in terms of its DC offset, or quiescent DC potential. So this signal is going to be seen by this resistor, and the current that flows through this resistor will change based on the size of the signal. Given that there's no gain in this stage, the size of this signal must be the same size, this voltage I'm discussing at the moment, the size of this voltage must be the same as whatever we find across RL. So if we decide we want 2 volts out, this is going to have to be 2 volts or thereabouts. If we wanted 14 volts out, it would have to be 14. And if it was, what was left for RVAS at the very top of the cycle would be not much. And that's one of the things you'd have to consider if you were designing this circuit. But leaving that for now, we want to know what is seen by the signal here looking upwards. And in the case of just a resistor, it sees the resistance. But in the case of this circuit, it sees something else. And we do the usual thing, which is we put a voltage source where the signal goes in. So this is the source is sort of trying to push a voltage onto this node. And we want to know what's going to happen to the small signal version of IC. And then we'll divide one by the other, and we'll get its resistance. And then we'll have the resistance looking in to this node, or looking up there, or looking up there if you prefer. And the analysis is reasonably long-winded, and I've put it in on the back of your lecture notes. Turn to it if you want, but you don't have to. Let's have a quick look, see what I did. It's important that I can't remember what I did. I know where I've got to start from, and I know roughly what I'm going to do. It's going to be a bit of Kirchhoff and maybe a bit of superposition if I'm feeling in the mood. But the actual result and the particulars of the analysis are gone from my mind as soon as they're done. Unless I do it really, really regularly, in which case maybe they'll stick. But it isn't important that they stick. So I don't remember what they are, and if you think that's a good approach to design, I fear it will not work out for you. You have to just be able to do the skills. I know it's very tired and I'm like a broken record, but back to this. Sum up the currents of the emitter. So this is like week 6, year 1. And we've got IB plus GMVB plus ICE is I. The only important thing that's different about this analysis is RCE. And I've included it because I know it's important. If we just assume that you don't know what's important compared to what isn't important, include everything. That will make the analysis much harder. No, it will make it much longer. But at the end of it, you'll be able to see which bits are important. And if you can't see it by looking at the equations, you can just insert some numbers, change them all by 10%, one at a time, and you'll figure out which bits are causing the differences. By when you change that bit, you'll know that the result changes a lot. Otherwise, textbook will always know what's important because they won't want to do any examples that are too long. So much like the textbook, I've included RCE because I know it's going to be significant. So then we just insert some voltages instead of the currents, except for GM VBE, because GM's a conductance and VBE's a voltage, so you multiply the two together and you get a current anyway. Yeah. It is too early, isn't it? And then you've got to remember that VE is minus VB, and you can see that by either looking at the diagram, and if you don't like the idea of looking at the diagram, what I'm really saying in 3 is that you sum up the voltages around this loop. Because those two are both grounded, there's a loop there. And if you add up those voltages, then VB must be equal to minus VE. So you eliminate one from the other and end up with 4. And then you've got to stop for a bit and do something else, which is sum up the currents at the output. So I'll have IB plus GMVBE plus ICE is equal to IE. So I just looked at all the currents flowing into and out of this node and added them up accordingly. And then you have to do some substitution where you put those two equations together and eventually an answer drops out. The only important bits are figuring out which loops to sum in terms of voltage and which nodes to sum in terms of current in order to get you towards where you want to be, which is the impedance resistance looking into this node here. Please go through it in your own time. If you don't, I dare say you're doomed. Anyway, the result of all that stuff is that R out is approximately equal to RCE times 1 plus beta. So 1 plus beta is quite large, 101 probably, if you say beta is 100. So R out could be pretty huge because RC is already in the order of 100 kilo ohms or so. So a nice big resistance looking up here, much bigger than RVAS. Notice also that this equation is quite small, despite the fact that I end up with a lot of big equations in the analysis. Towards the end I start making assumptions which allow me to make a small equation. I don't want an enormous equation where I have to sit there and go, well, what are the key terms in this? That's not a very good idea. You want a nice small equation that tells you what's going on pretty quickly. Right. Happy with the idea of current source? Want to hear it again? Wish never to hear about small signals again. Right, no more small signals in this bit. Well, not many. We have a situation where this circuit here, this stage, has to drive these two transistors. And in order to do that, it needs to supply them with a certain base current, both the quiescent base current and the signal base current. And we can think about the signal bit as the resistance looking in T4. This is T4 base, so looking in here. This business, IQ9 and, oh damn, sorry. They're supposed to be T's. In my head, transistors have Q, not T, because there's a software program that I really like to use that calls them all Q. And sometimes I slip. So that should be Q9 and that should be that should be T9. I'm not doing it. T9, IT9, T5 and T4. This IQ is right. Q here is for quiescent. So the resistance looking into Q4 is, I've worked this out and I've not bothered to derive it. RBE4 plus the beta of that transistor plus 1 all times the external load resistance value. So earlier when I said, oh, well, it's just an impedance transformer, and what you see at the output changes what you see at the input, here is, well, it's not quite proof because I didn't derive it, but an expression that is the result of proof. You've got input resistance, Ri4, resistance looking in there, is equal to a load of stuff, including the size of this resistor. So if I had a 1K load resistor in some sort of, I don't know, detector system for measuring some semiconductor or another, I would see a certain resistance looking into a Q4's base. On the other hand, if I had an 8 ohm speaker, I'd see a different resistance looking into Q4's base. We can make what the voltage amplifying stage, which is just off this diagram, this bit here, we can make what it sees looking into T4 and now Q9 and IQ9 as well, different. And the addition of Q9 or T9 or whatever is there for that purpose. Essentially, Q9 forms a Darlington with Q4 and has all the advantages that we had for the voltage amplifying stage. That is to say, its betas multiply and so do its HFEs. And it forms a Darlington with Q5 as well. Now the fact that one's NPN and one's PNP doesn't matter. It makes no difference at all. As far as the signals are concerned, transistor's a transistor. There is no PNP or NPN. The only thing that matters is the polarity of the biasing voltages and the quiescent currents that flow. As far as the signals are concerned, the transistor is just a thing that they end up in somehow and want to get out of. There is no difference, NPN, PNP, it doesn't matter. So the point of IQ9, we could make IQ9 a resistor and it would be the same thing we've got up here, with, well, not quite the same. This is emitter follower and it's being loaded by a current source. We could have emitter follower loaded by a resistor, that'd be fine as well. But for all the reasons that we gave for having a current source here, we will also put one to load Q9 and we'll also put one to load RE in the differential stage. So if you want to know what the input impedance looking here is, you could make a giant small signal thing of those two and work it all out, and that'd be fine. Or you can just say, well, look, I've got a resistance looking in here, and I can call this just a resistor, and I'll call its resistor Ri4, and then I'll work out the resistance looking in here, due to this circuit with just a resistor Ri4 hanging off this node. And if I do, I'll get this equation, which is the same form as that one, which is hardly surprising because this is emitter follower as well. In that case, if I want to know the resistance between here, I'll sub 1 into 2. 0 extra effort, pretty much. Do you follow what I said there? Or do you want it again? Again, please. Right. When I was working out the resistance looking into Q4's base that a small signal sees, I came up with this expression. And this on its own is emitter follower, or common collector if you prefer. And I worked out that it was proportional to the RBE of this transistor, each beta, and the external load that it sees, which is there. And this is what allowed me to arrive at 1. Well, as this is what the answer is, and that's a description of it. If I had another common emitter, common collector or emitter follower circuit driving this emitter follower, its resistance looking into its base, given a certain load hang off here, will be the same form as the original expression. It's the same circuit. There's only one answer for any particular circuit, assuming you make the same assumptions. So if I just call Q4 and all the other stuff a resistance, and I call that resistance the resistance looking into Q4's base, I've then got Q9 with a resistor hanging off it, which is just the same as Q4 with a resistor hanging off it. So instead of beta 4, RB4 and RI4, I've got RI9, RBE9, beta 9, and instead of the external load, I've got the resistance looking into the next stage. You can just bolt them together. Let me draw another diagram. My first arrangement is this one, where this is RLX, and I'm looking at the I'm trying to get I'm going to drive a V in and measure this current and work out what the resistance is looking that way. This is T4. And once I've done that, I'm going to use the same circuit, but instead of T4 and RL external, I'll change this to be the resistance I just worked out, which is RI4. This will become T9. That will become a different current, and I'll just put a voltage in. And I'll do the same working out, and it's the same circuit, so I'll get the same equation, just with different letters in it. So I can bolt the two together. Can you really bolt the two together? Yeah, pretty much. The fact is, there is a slight... It's not that you can totally decouple what happens on Q4's emitter from Q9's base. There is still some effect of the external resistance on the current that's required to flow into Q9 as a signal to develop a particular voltage there. But that coupling is greatly reduced by a factor of all this stuff. The dominant part, which is beta 9 plus 1. Better? Not better. Somewhat better. Oh, here we go. So, this is, if you can't tell what I'm up to, have a look here. In all my notes, that's where a brief summary of the slide is. So, these are carefully chosen words, consequently I'm going to more or less read them. So there's a higher resistance looking towards T3's collector, and that acts to increase the output resistance of the amplifier as well. So going back to this for a bit, if I was a signal here trying to get back into the rest of the amplifier, I'd be thinking about RVAS and the impedance, the resistance looking into T3 or T8 and T3 if it was there. And if I had a current source here, RVAS would be much, much bigger than it would have been if it was just a resistor. And a couple of lectures ago, we simplified the impedance, resistance looking out of the collector to RVAS because it was the smallest resistance out of RVAS, the resistance looking at T4, the resistance looking at T5, and some others as well, probably. And if you go back into the notes and have a look. Now we've made RVAS big, it is not the smallest of all these resistances, and the assumption that we can just say, oh, well, the resistance looking onto this node is RVAS doesn't hold anymore. We have to worry about what other resistances there are. So the higher resistance looking towards T3's collector acts to increase the output resistance of the amplifier as well. So the coupling that I just described between what happens with RLX and the size of the signal you need here to produce a particular waveform here acts the other way as well. Looking in here, I see a small portion of this resistance. Looking in there, into this node, I see a small fraction of whatever happened here, or a fraction. So the impedance to resistance transformation works both ways. So that's what I've said in the top line. And the output resistance of an emitter follower is approximately equation 3. So now I'm saying what happens if I drive make this T4 again, get rid of that and that. Oh, I did it the other way up, didn't I? No, sorry. Close enough. I'm going to assume T5's off and therefore doesn't play any part and only worry about what happens to T4. So we'll assume that the signal that's currently in this amplifier is that one and not the other one, because the other one would be dealt with by T5. So I'm worried about a voltage called Vin and a signal current called In, if you like, but this is secretly the output. I've taken off the load resistor and I'm driving a signal in. And we want to know what resistance we see looking up here and a small fraction of the resistance we see looking up here. Now, for a biscuit, what does it approximate to? If you get it, I'll be really impressed. If you've got yet last week's notes, it was in there. It's approximately resistance looking into the emitter of this transistor will be 1 over GM. But it's approximately. And that's the thing, because a small part of that resistance looking up there is due to whatever happens on the base. And that involves the size of the current source, resistance looking into the current source and the resistance looking up there. So this impedance resistance transformation works in both directions. So we end up with the output resistance is RV over beta plus RS over beta, where RS is the source resistance. So I'm lumping all this stuff here, into just a resistor, in series with the base. So without T9, back to this situation, well nearly that situation, the RS for T4 is the collector load of T3, so whatever we've got here, be that current source, resistor, whatever. Now, that resistance has been made very large in order to maximise the gain of the voltage amplifying stage. That's to say I chucked out the resistor and I put current source in instead, for the reasons that I gave earlier. Now this will increase the output stage's output resistance, so the resistance looking into the emitter of T4. Same analysis applies for T5, just the other way around. So if we include T9, this allows the resistance of the output stage. When I say the output stage, I now mean T9, T4 and T5 to be large. Sorry, the input resistance of the output stage to be large. That is to say, only a small current is required in T9 to make stuff happen, T9's base to make stuff happen. And it simultaneously allows the output resistance to be small. If you prefer, you can say it's got a big current gain. your choice. So these two problems, firstly, the low input resistance of the output stage before we added T9, and secondly, having increased the source resistance, that's to say, made this much bigger because we put a current source in, of T4, we have a situation in which the resistance looking into the output stage has gone up. That's because the coupling works both ways. So these two things, when you look at them from both directions, say a lot about what a transistor really does. That is to say, it just transforms impedances, or if you prefer, a transfer resistor, which is how it comes to be transistor. Adding T9 improves the resistance transforming property, or if you prefer, increases the current gain in the output stage. Same thing. That is all I have to say about output stage. As I said, it's not easy. I don't think I actually clicked that until I was into my PhD. Don't panic though, it's fine. So, last thing to do with this circuit, I've already put this business here, which is an amplified diode. That's what it's called if you want to Google it. And the reason we need it, this should be fairly familiar now because it's in the amplifier lab. We need it because we have a bit of the signal in the middle which is lost, that little flat bit, and it's in the prior slides as well. The way it works is we insert this transistor and we have a VBE here, and this VBE must fall across R10. There will be 0.7 volts across R10, and if we choose R10, we're choosing the current in R10 as well, which I call IR10. And if we assume there's no base current in our T10, or Q10 if you prefer, then this IR10 must also flow in R9. That being the case, I can choose a ratio of R10 and R9 to produce a particular voltage between the collector and emitter of Q10. So if I made that a kilo ohm, then I'll make it 700 ohms actually, much easier. Then a milliamp will flow because I have 0.7 volts due to the VBE. And if I made that 1400 ohms, I'd have 0.7 there and 1.4 there, and that would give me 2.1 across the lot. Follow or no follow? Mostly follow. Not really though. So, this resistance falls across this base emitter junction, so its voltage is pinned to the VBE. There's no danger that the voltage across R10 will be anything other than 0.7. Now I'm going to assume that we're not silly enough to make R10 0 ohms, if you pick a reasonable value. So there'll be a current that flows in R10 which is proportional to its value, which I've chosen. Well, really what I'm doing is choosing the current and then working out what R10 is going to be. And then I'm going to say, well, I've got R9, I want 1.4 volts across here. The reason I want that is because I need 0.7 for this base emitter and I need 0.7 for this base emitter. And if I do that, they'll both be switched on all the time, and there'll be a very small current that flows from the top down to the bottom. And that will stop me from ending up with these little flat bits. Both transistors just about turned on. And in the amplifier lab, when you were turning that little potentiometer, it was actually a variable resistor in R10's position, and the meter, analog meter you had, was measuring the quiescent current that flowed from the top to the bottom, because the meter lived up here. So we want 1.4. If you increase that, you'll turn these on more and have a bigger quiescent current, and that was the effect of turning up the knob. So VB 0.7, I've decided a milliamp just because it makes easy numbers. That means I need 700 ohms here. Right? Right. And I'll have 0.7 from base to emitter. Now from collector to emitter, I'll have, well, from base to collector if you prefer, that'll be reverse bias, so we don't know what this voltage is going to be, and it's not limited by this junction. But we do know that IR10 ought to flow in R9 if the base current is neglected. And we will make the current that flows in IR10 sufficiently large that we know we can neglect the base current based on a guess of a HFE of 100 for Q10. So base current goes away. If you want to include it, you can, just make your equation slightly longer. So we've got a current that we've defined, I've made it a milliamp, flowing in R9, and we want 1.4 volts across. If I make R9 the same size as R10, I'll have 0.7 volts across it. When I say size, I mean resistance. In which case, I'll have collector to emitter as 1.4. If I make R9 twice R10, I'll have 2 VBEs across R9. And if I make R9 3 times R10, I'll have 3 VBEs across R9. And that's how it comes to be called amplified diode. You get a number of VBE drops if you use multiples of the, if you integer ratios of resistors. Happy with that? Right then. So this is our finished thing. That's all of it in all its glory. And this is a reasonable attempt at a decent op-amp. It'll give very good performance actually. And if we went to some op-amps from, I don't know, 1970 onwards, they'll look pretty much like this. In fact, I've got some op-amps from 1970 onwards. Oh, I've got a few other things as well. There's one. So for a biscuit, because we've only got a couple of minutes left, I will come back to whatever those other slides are. Can you point out any bits? It's made up of bits that are familiar. It's just quite a big circuit. So I've got biscuits for circuit blocks. Hmm? This one? This one?
Yeah.
This one?
Yeah.
Yeah? What of it? Come on. That's not worth a quarter of a biscuit. You've got to say something sensible about it.
Output stage.
Output stage. Unfortunately, it's come to get you. All this stuff here is just one massive current source. Output stage is this bit here. How about this bit? It's a Darlington, definitely worth a biscuit. A biscuit for Darlington, it's like being. So, what about this bit? In fact, that current mirror. We've got to give the biscuits to him. So, these are JFETs, but it doesn't really matter. What is it? Differential amplifier. There seems to be a lot of biscuit activity down here. So, alright then, if you're keen on that, how does this work? This is not something you've seen yet, but it ought to be fairly obvious what its job is. Firstly, what's its job? There were 3 different answers then. You are correct. If you didn't hear it, it's a thing to bias these 2 bases apart from each other. But they haven't used as many resistors as I have. And the reason is that making a resistor on an IC is jolly expensive. You have to deposit a couple of extra layers, and if you want a particular value of resistor, you've got to trim it with a laser, which means you've got to pay somebody to calibrate your laser, bring a machine into your production lines, lots of extra effort. It takes longer to make the part, that's the most expensive bit of that. So if you can, you'll get out of putting any resistors in, and you'll try and use transistors always, and diodes and other things that's easy to grow, especially if you're going to grow them anyway. If you've got too many transistors, you can just pick up a couple that are laying around. There are reasons why you might want extra transistors, but I don't want to get into them now. So this has got its base and collector connected together. So what is it? Test your mental malleability. No. Now I've got a 3-terminal device made up of 2 junctions, and I connect 2 of those terminals together. I can only use the other junction. What have I got? A diode. It's just a diode. It's meant to produce 1.4 volts across there, and this is meant to produce, 0.7 volts across there. There'll be 0.7 across there. This resistor sets the current in that transistor, and I end up with 1.4 volts across that bit. Right. I think I'll leave that on for now. I'm a bit late anyway. So, there will be... I wish I could lecture during the tutorial, but I'm away that day. We will finish this next week and shuffle on to ways of using amplifiers.